for our participants. Over to you, ma'am.
Thank you for inviting me to deliver this talk. I think I have heard my previous speaker, and I'm pretty sure the earlier lectures have discussed a lot about satellite meteorology and its applications in the field of meteorology. What my biodata doesn't say is we are pretty much the last line in the chapter of meteorology, in the sense that we have to implement whatever people are producing or new products that are coming up. So pretty much the proof of the concept or the proof of the pudding is to be delivered by IMD, India Meteorological Department, and hence we have it is a different kind of work compared to just publishing a paper and ending it, because here we survive on accurate forecasts, and if forecasts go wrong, I think many of you join the others in saying that ये सरकारी department कुछ नहीं करता है. So keeping that in mind, I will discuss about how we are using satellite-based satellite data for weather forecastings, with special emphasis on thunderstorm forecasting. So if you see thunderstorms, when we, I just wanted to give you only one slide of this. Every cloud, every convection is not a thunderstorm. This is something we have to keep in mind. The first stage is cumulus. If there is enough supporting factors like enough moisture, a wind discontinuity, the synoptic systems, orography, something else has to be there for this cumulus cell to become a cumulus congestus. This is the second stage of a cloud development. I'm saying of a warm cloud development. Many clouds end their lives as cumulus congestus, in the sense that you get rain from such clouds, but the process of thunder does not start in such clouds. The next stage is where the cloud crosses the 0 degree Celsius, the 0 degree isotherm, and droplet formation takes place inside the cloud. You get electrification of cloud, you get lightning and thunder. So this is a thunderstorm. Our job is, even before a cumulus has formed, to give a prediction for cumulonimbus stage. As you can imagine, this is a very complex job, and the job is not as simple as maybe say giving a rainfall forecast, which is a graded thing. Like if you are saying there will be rain, and if instead of 10 centimeter, 5 centimeter happens, you still did something right. Here it's pretty much a 0-1 case. If you say thunderstorm is likely to happen and thunderstorm does not happen, you are wrong. There is no 0.5, 0.7% right or wrong. Keeping that in mind, we have to now discuss how satellite data is used for thunderstorm forecasting. So when I started to prepare my talk for this particular series, I thought in what way to separate it out. So this is my understanding, on the basis of which I have divided up into 3 categories. First is detection of thunderstorm supportive environment. This is a very important aspect where we are using satellite data. Satellite data is one of the biggest supports for this part of the job. Then the next stage is assimilation into NWP models. I just caught the end part of my previous speaker's talk. So as you know, that assimilation into NWP models is a very significant aspect of use of satellite data. And I'm not talking of NWB models in general, but also mesoscale NWB models, which take the initial conditions from global NWB models, which in turn take in the and where satellite data is assimilated in both the mesoscale models as well as global models. Satellite data in per se forms a very significant component of the second kind of usage of satellite data. The last category is detection of occurrence of thunderstorm, which is the direct measurement of thunderstorm. Can we do that? If yes, what are the accuracies? So, and then the final way of bringing everything together into what is our job, which is what is the job in the division in which I work, is thunderstorm forecasting. How do we use the detection of thunderstorm supportive environment, the NWB models in which satellite data has been assimilated, and the thunderstorms that are detected by satellites? How do we use all this information to improve our thunderstorm forecasting? So when we talk of the first component, that is our detection of thunderstorm supportive environment, what do we look for thunderstorm supportive environment? We look for winds, your atmospheric motion vectors, visible IR water vapor channel derived atmospheric motion vectors, CMVs, WVW. The other thing we look at is, say, scatterometer winds, which is surface winds. You have a surface location of a low pressure system on the sea. How do you think we give a location that it is currently over at 17° north and 8° east? It's a sea. I presume it's a sea. I didn't check this exact value. But there the scatterometer pass forms a very significant support for giving us the winds detected, the wind speed detected gives us a very good indication as to what is the actual strength of the weather system that over the sea where we have no other observations. Atmospheric moisture boundaries, I'll just show you one example of it. Atmospheric moisture incursion, this is again another thing we look at. I mean, total precipitable water, in what way it is entering, exiting. Vorticity, divergence, convergence. Very significant facts, especially for locating synoptic systems and vertical shear. Anybody who's worked in tropical cyclone forecasting knows the importance of satellite-derived vertical shear in understanding whether a system is going to grow, decay, move. Everything is very dependent, and direction of movement dependent on the vertical shear. I'll just show you one example. It was when I was making the presentation, this is exactly what we do in operations. So that day's data, 1st of August, I picked it out, and the way we did the forecasting was just one weather system we'll discuss. Say there was a western disturbance. Now, if you draw a line, and this is a western disturbance, is nothing but a westerly trough. It is at 500 HPA, so roughly around 5.8 kilometer. So we just had two winds. One was Patiala wind and another was over Iran. Now, based on these two winds, we have to give the strength, location, and the way in which it will approach the Indian region. That would decide the forecast for the day. Which region would get thunderstorm activity, convection? Everything will be decided on the basis of just two winds. So what do we do then? We look at the satellite data. Now, this is the water vapor wind from INSAT 3D. If you look carefully, this location is given as a, you can see the water vapor boundary, moisture boundary, if you see, it's very clearly showing a troughing situation northwest, further to the west of the Indian region. And if you see, it is tilted. That means it has the northern part of it is further to the east, and the southern part is further to the west. So these two images then combine together to give the inference of this particular weather system for the day, which means we had a tilted westerly trough, which was located from 75° east, 38° north in the north, and in the south, 63° east, 27° north. So that means the southern end was further to the west, northern end was further to the right. Just two winds that we got from radio sound observations was not sufficient to give this much of detail. If our weather forecasting has improved in the locating the weather systems and intensification of the weather systems, it is mainly because of the satellite data, which has allowed us to actually assign the more features than would be possible just based on, say, the radio sound data. The other aspects that I talked about, atmospheric moisture incursion, vorticity divergence, I'll show you with an example later. If we now look into assimilation into NWP models, which is the second most important aspect of use of satellite data, I'm discussing this aspect not because we are directly using it in thunderstorm forecasting, but we are using numerical models. So these numerical models are all customized, or are the best first guess conditions are all derived on the basis of data assimilation. Just as an example, I'm showing you ECMWF data improvement. 3-day forecasts, 5-day forecast, 3-day forecast is in blue, 5-day forecast is in red, 7-day forecast is in green, and 10-day forecast is in yellow. Simultaneously, if you see in this, the upper curve is, say in the blue curve, the upper limit is northern hemisphere and the lower limit is the southern hemisphere. You will note very clearly that post mid-1990s, there has been a very sharp increase in the improvement of the model forecasts at all time scales. And another thing, if you note in this particular figure, the difference in the accuracies of southern hemisphere versus northern hemisphere was pretty high prior to this period, and following 1997-98, the forecast accuracy has become almost similar for northern hemisphere and southern hemisphere. Why do you think that happened? A very important aspect of the globe, if you understand, is that most of the land region is to the northern hemisphere. So we have a lot more data in for land-based observations over the northern hemisphere as compared to the southern hemisphere, where large parts are the sea. It is only after the assimilation of satellite data that we could give a forecast of accuracy similar to northern hemisphere for the southern hemisphere. Why does it affect us? Because the globe does not exist in terms of hemispheres. If the forecast of one hemisphere is of half the world is wrong, the other half cannot be better. And this is what this difference has decreased, and it has become almost equal to each other. It is only after 2000. This is the NCMRWF. I quoted the paper from which I have copied these slides. So the first one is by RISCO. The paper's reference is given. The second figure is from NCMRWF. There was a very beautiful paper in Mosam by V.S. Prasad and his group in NCMRWF. Can you see this pie chart? If you can read it carefully, you will see that a very thin slice of this pie is from surface radio sound observations. Very thin, dry orb, which is shown, is very thin part of it. Aircraft constitutes another very small component, but the major part of this uh, pie chart, so to say 97 to 98% of the data, which is currently being assimilated into NWP models operationally, is from the satellite data. Different kinds of satellites, ERC, AMSU-A, AMSU-B, IIRS, all these data are a very significant component in the assimilation and creating the first guess, the analysis field for modifying the first guess field for analysis, creating the analysis field for forecasting. So this indicates the importance of satellite data for improving the NWP model forecasts. This is not just in the global scale. If forecasts have improved, it is simply because this vast amount of data is regularly being incorporated in global models as well as mesoscale models such as WRF. When we talk of the detection of occurrence of thunderstorms, here we are not talking of only the thunderstorm supportive environment or assimilation. When we are talking of direct assimilation, direct detection, I will be quoting a few papers that have worked on this. For example, precipitable water vapor in the atmosphere. So this can be in the first as well as in the third, but I have kept it in the third. But sudden change in precipitable water vapor over a station is an indication that convection is likely to happen. I would not say this is an exact one-to-one correlation with thunderstorms. Like I said in the first slide itself, the cumulus to cumulonimbus transition is a very is full of lot of ifs and buts. So, but nevertheless, the first sign of convection often comes from precipitable water vapor. This is from the NAVIC group of satellites. It's an ISRO paper. So Indian Navigation Satellite Network, the Seven Sisters, which monitor give the location of a person, and accordingly it also gives you the delay in the propagation delay, also gives you an indication of the precipitable water vapor in the atmosphere, and hence you can calculate if there's a sudden change that gives you in the column, it gives you an indication that yes, convection is likely. Why is convection likely? Because, and the principle is the same in the figure in the right also. Why is convection likely? Because Indian mainland we are in the tropics, and there is a very significant, I mean, this temperature is generally high over the entire Indian mainland, and tropical convection is pretty much a function of the moisture arrival. So both these function on the same, that is, increase in precipitable water vapor indicates an increase in convection. Of course, it does not say it will be thunderstorm or just rain from cumulus congested stage, but nevertheless, it is a good indication of convection. The other thing that many studies have found that is the use of microwave channel sounder payloads. These payloads can penetrate right through the cloud, and they measure something known as cloud optical depth. There is a threshold they have found, especially this was found for over China, that cloud optical depth threshold at the convective initiation stage. So when you're talking of cloud optical depth, it means you are, if there is a threshold, it means the opacity is increasing. It means the cloud liquid droplets are increasing in size. So there is a threshold, and microwave payloads are very well capable of detecting this threshold. The advantage is, naturally, it can penetrate through thick clouds. It can penetrate through cirrus, big thing for us. And even the precipitation within a cloud due to weaker atmospheric, and because of the weaker atmospheric extinction coefficient effect for the microwave channels. Disadvantages, microwave data from polar orbiting satellites. Their polar orbiting means they have uh, less sampling time over any region. So it's good in the climatological context, but not so good in the operational context. Then hailstorms. Again, the principle is similar. The brightness temperature measured from the ANSRE satellite Aqua and the brightness temperature from the TRIM microwave imager, both are used to and calibrated against measurement of hail. This study was measurement of hail over United States and then applied to the entire country, to the entire globe to get a hail climatology. Why do we need such a climatology? This has an importance because even in the climatological context, people want to know which are the regions which are more prone to hail. This is not just an academic requirement. A farmer will plant his crops, he will take precautions whether he will needs to buy a hail net. When should he keep that facility available? People use hail guns. When should he use the hail gun? So all that is found out only when we have a climatology. So they found a very nice climatology which indicated during March and April, the climatology indicated high hail frequencies over East India and in July, August over Northwest India. So here again, there is a disadvantage being that East India, fine, but this hail climatology did not pick up the frequency of hail that you see over the Himalayan region. If you've ever gone to the Himalayan, these fruit growing states of Himachal Pradesh and, where fruits are the main crops. So there you'll see hail nets are very common. You don't see so many in the plains because hail is really a fact of life there. Entire apple crops can be damaged with a single hail incidence. But this particular method is not capturing that. It is showing a hail maximum over Pakistan in July, August, and we all know that really there is not much hail. So that is coming primarily because of the inability to distinguish between hail and droplet concentration. So this is picking up more of the lightning aspect of the cloud rather than the hail aspect of the cloud. So these are problems with anything that is detecting from above. Then measurement of cloud top brightness temperature of developing convection. This is the most commonly used product. That means you just measure the cloud top brightness temperature. Presume that 240 Kelvin or minus 243 Kelvin or minus 30 degrees Celsius cloud top temperature corresponds to convection happening. But there are problems. The benefit is its high temporal resolution, geostationary satellites. So these geostationary satellites, they measure the height, have a 30-minute, or if you have INSAT 3D and 3DR, then you have a 15-minute interval sampling of the Indian region. The disadvantage is it is difficult due to complex and unpredictable trigger factors. There is a large false alarm rate. I'll show you a slide next to it. So when you're talking of, say, satellite measurement of, say, cloud top brightness temperature, it is basically measuring. If you see a cloud, it comprises something like pistons, like they're putting out moisture in the upper atmosphere, multiple pistons, multiple small cells within a large convective zone. So immediately above the cloud, you will have cirrus, and then it spreads out. As a result, what happens is generally, it has a problem. The problem being, it presumes that all clouds are putting out or pumping up equal amount of moisture in the upper atmosphere. This is not so. Please take it. Cirrus outflow is only a concept during monsoon season. Pre-monsoon clouds, very rarely do they have enough moisture to pump out unless there's a large scale system giving it day-to-day convection. Oftentimes you might have a convection. Firstly, the scale is very short, spatial and temporal. The second thing is moisture is less. So such clouds, they may reach up to the top of the atmosphere, but their breadth is only 8 to 10 kilometers. So 10-kilometer wide cloud will not really give any signature at the top. Why? Because it doesn't have enough moisture to carry it up and throw it into the upper atmosphere. So these often go undetected. So single clouds, pulse storms, supercells also, especially during pre-monsoon season, are very poorly detected by this method. On the other hand, monsoon convection, when the cloud has a lot of moisture, it has a huge, the lifetime of the cloud is long, and breadth of a single thunderstorm cell is maybe 50 to 60 kilometers. So such clouds will pump a lot of cirrus, a lot of moisture into the upper atmosphere, and you might get a large cirrus overlay as compared to what is actually happening. So there you have a problem of overestimation. Underestimation during pre-monsoon season, overestimation during monsoon season. But nevertheless, large-scale movement and evolution is very well detected by this method. Again, I'll point out to you, we are the operational meteorologists. If any of the products are not available, we cannot sit back and say no forecast. If we have to give nowcast scale forecasts for thunderstorm, it has to happen throughout India, whether there is a radar, whether there is any other observation or not. So satellites there prove to be a very important tool for evaluating whether there is thunderstorm happening or not. This is an example of INSAT 3D on 8th March 2017. This was from the paper that I have quoted here, Goel, Sitka and Tyagi. So this showed that when there is a large scale clouding and you have, when there is a good synoptic scale system, you have very well, it picks out which is the region, the cloud top brightness temperature, the minus 20, minus 30 degree Kelvin, minus 20 degrees Celsius contour that has been drawn, and minus 30 degree Celsius contour that has been drawn, very well picks out which is the region for thunderstorm occurrence. So if you really see here, please go around, say this was taken around 9 UTC, and to the right you have 6 to 12 UTC, whichever stations reported. You will see that is mainly East India, but East India, again, you please note, it is not really, all the cells have not been detected. Puri, Keonjhar, Balasore, these cells have not been detected by this method. The other thing is, this threshold that we are considering, say minus 20 or minus 40, is a very subjective threshold. It might work for cold clouds, but oftentimes convection happens. Even I will not say thunderstorm, because thunderstorm, it requires minimum of minus 20 degrees Celsius. It should go to the negative side. There has to be a cold cloud component. Only then ice formation will happen, droplet formation will happen. But convection might happen without thunder for even 280, 290 degrees Celsius. So purely warm clouds, say the west coast, North India, you might get warm clouds also giving you rain, and that will not be detected. But yes, thunderstorms, this has a better understanding. Keeping this in mind, the fact that geostationary satellites have a good footprint and high temporal resolution, combination of satellites have been used globally to produce uniform products all around the globe. This is from a WMO picture. So if you see here for Indian region, it does pick out the INSAT 3D also. And other than INSAT 3D, there are multiple satellites which 3D, 3DR. Other than these two also, there are multiple satellites which are sampling the entire global tropics, especially exotropics. Your pixel resolution is decreasing, so that is a problem. But especially for the tropics, where we are fortunate, a lot of satellites are monitoring. So if you see from these satellites, like this is from the WMO site again. So please do not look for the INSAT 3D. It has not been integrated into this product. But Himawari, which is the Japanese satellite, GOES, which is US, Kengyun, which is the Chinese satellite, GeoCompsat, to see that, and Meteosat, third generation. So all these satellites have similar products being generated. So these can be combined to form a global composite, and nowcasting can be done. Scope nowcasting is one such product. There are many such products that are being derived. Within ISRO also, people are working on these algorithms. These softwares basically work on the principle of pattern matching and forecasting. So it takes the 30-minute earlier picture, takes the current picture, sees the intensification, de-intensification, sees the movement, and gives a extrapolation. The method of nowcasting is extrapolation. So where there is no other tool available, this is a global tool to form background for forecasting. So the other thing that we also use operationally for thunderstorm forecasting is the signatures in the thunderstorm, signatures of thunderstorm in the data. So far, we have discussed about the cumulonimbus stage, whether the satellite is detecting cumulonimbus stage or not. But even at the cumulus stage, our present generation of satellites is very well capable of giving an indication where thunderstorms are likely to happen. So this is a very nice picture of the cumulus stage. This is the early mornings. I'm sorry, I have missed up the time. And this is the data around 4 hours later. So if you see very clearly, you see small reddish colored pimples. Like on the face, you get pimples, you hate them. But here we like the pimples because these show us where the cells are forming, which are the places where we have to monitor. But again, please remember, each of these cumulus cells does not result in cumulonimbus. So this forms one of the products to look at for a forecaster before he gives a forecast. Then Meteosat RDT. This is another product available to us for rapid developing thunderstorms. Whether we are able to locate thunderstorms, which are the developing thunderstorms, it gives us. Divergence, convergence, I talked to you. Another thing I want to show you is another place where thunderstorm forecasting is really benefited is over the hills. IIRS Dehradun is definitely Dehradun is a very crucial spot for thunderstorms, especially during this season. Why is it? Is because it is during the monsoon weak conditions, like currently trough is in the foothills, so Uttarakhand gets a lot of rain. So what really happens, this is something that is during the pre-monsoon season also. You will note that these cumulus cells that I talked about, these start forming, say at 7:45 IST. You will note that cells first have started to form. This is the Himalayas, and they've started to form just along the foothills of the Himalayas. Nothing is happening over eastern parts of the western Himalayas. That means Uttarakhand is nothing. We can say okay, within 3 to 4 hours, let us see what happens. These cells have started to migrate southwards along with the katabatic winds. These cells have started to move southwestwards towards the more plain regions. As a result of which, thunderstorm occurrence has started in the over Jammu and Kashmir within by about 10:45 IST. But at 10:45 IST, if you see very carefully, little cells have started to form here also over Uttarakhand region. So what does that help us with? When an operational forecaster has to give a forecast, he or she looks at where the cumulus cells have started to form. Then he or she looks at what are the synoptic conditions, whether these cells will become cumulus congestus and die down, or whether they will become cumulonimbus. Fortunately, on this particular day, just this product is sufficient to show you that yes, all these cells could become cumulonimbus, and they gave rainfall, thunderstorm, not rainfall, thunderstorm activity further to the south, which is over your Dehradun and Shimla and this Jammu. So all this cloud that formed in the upper reaches, or rather the foothills of the upper Himalayas, moved southwards and gave thunderstorm activity. But this is a good indication for us, especially during the nowcast scale, when we need to give a forecast, even in the absence of other products. This becomes a very good tool for forecasting. And this is what was recorded in the lightning product. This is something in the middle of the presentation. I've kept it because this is a talk on satellite meteorology, or satellites, their use in meteorology. We also have a satellite meteorology division. I was in the division for 8 to 10 years. So oftentimes, and maybe it is with me, but I believe it happens with anybody with some passion for the work, you tend to believe that if you have a hammer, everything looks like a nail. Okay, so if you have satellite, you believe all problems can be solved with just the satellite. Why I talked of the disadvantages of each of the satellite products is, you must remember that nothing exists in isolation. If we are using satellites, or rather the way we use satellite data, it is not only satellites which are improving our forecasts or which allow us to do forecasting. Satellites form an important part of the composite of IMD's forecasting standard operating procedure. This is true for, and this I will advise is, you, if you are trainees, you will go back and start working with satellite data. Please do not be focused in reaching from point A to point F always through the road of B, C, and D. Oftentimes, you will note you have to reach from A to F by moving from Z, Y, X, and so on. So, and those things may not be necessarily present in the satellite data that you're working. So you need to consider every other source of data if you're looking at a meteorological phenomenon. So when we're doing thunderstorm forecasting, we basically work with standard operating procedures. So this is our standard operating procedure about how, this is a nowcast SOP I'm displaying to you. Similar for thunderstorms, similar SOPs exist for detailed hail forecast SOP, squall forecast SOP, but for each of these SOPs, you will note that two things I have highlighted out here. One is this orange background blocks. These are versus the green blocks. The orange blocks are what a forecaster needs to see much before he or she starts the forecasting process. That means they need to see the climatology and extremes for the station, for their location, synoptic features which have been discussed in the daily VC, which have been discussed, which are, and the evolution which has been seen, freezing level, atmospheric profile, everything you need to see in model forecasts. Then he or she starts with the actual nowcast of thunderstorms. Here you will see I have marked many of these blocks. Inside the blocks, the figures with red. The writing is in red. The writing is in red, which indicates which of these is very much dependent upon satellite data. Synoptic features, I just showed you an example of a western disturbance. Freezing level, your sounder-based T5gram, where you have no radio sound data, you can extrapolate from take the systematic bias into account, you can get an idea about the freezing level. Model forecasts, I talked to you about data assimilation into NWP models and how it has provided a very paradigm shift in the accuracy of the NWP models. Weather already occurred. When we are seeing the satellite data in animation, we get an idea about where the system is evolving. If there is, even if you're not able to give the exact area, is it moving eastward, northward, southeastwards, northeastward, southeastward, eastward, where I'm talking about westerly weather system? That gives you an idea that, okay, if the weather has occurred, it is now moving to the east. Whatever has happened is moving eastward. So that gives a very good indication. Nowcast models have included, because please remember, no model is existing in isolation. Scope Nowcast is one product which is directly using satellite data. But if you're saying HRRR, EWRF, these are the models we are using for mesoscale weather forecasting. These are taking the initial conditions from global models, which are using satellite data. WRF model, it is directly assimilating satellite data. So all those data are used, and hence it is marked in red. Satellite data and products, I showed you a few examples where from the cumulus stage itself, we start monitoring satellite data, monitoring a cumulus cell, and considering every other factor, we say, okay, over my region, this cumulus cell that I'm seeing, within 3 to 4 hours, yahi bada hoke doctor engineer banega. So this will become a cumulonimbus, it will give a thunderstorm. So this is the idea of the satellite data. Then lightning data and products. This I have not displayed in as much detail as I would like, but from Meteosat, from JMA, we do get satellite-based lightning with less accuracy, but nevertheless we get it. Penguin satellite, we get satellite-based lightning. So this gives an idea of where convection is actually happening within the cloud. So even if you don't have a radar, we have a lot of radars, but there are still radar holes. So even if you don't have radars, the combination of the second last and third last steps can give you a very good indication where convection is happening, how it is moving, and what will happen in future. The last block is in black because this is dependent only on radar data, which gives you an idea of the intensity and quantification of thunderstorms. And finally, impact information. Impact information, we also have to give where there are no observatories. We have to depend on satellite data. And again, I'm telling you, satellite-based damage data is a very important component in deciding the impact matrix of the forecast. I will show you an example of a case study of 12th January 2022. This is just a small case study just to illustrate how we are using it, data. So there was a western disturbance, and over East India, we were more interested. Over northwest Uttar Pradesh, there was a cyclonic circulation, and okay, there was cyclonic circulation over southwest Bay of Bengal, and in the west coast there was a trough from in central India there was a trough, South India, Karnataka to South Chhattisgarh in the easterlies, and of course to the west there was over South Konkan there was a cyclonic circulation in the lower levels. But what I wanted to really show you is, when we are talking of the SOP, it is a very systematic way of doing. So we have firstly the model products, whether already occurred, I'm not showing here. So model forecasts here is global model forecasts. For a nowcaster, his job will primarily start from here, whether already occurred, to HRRR and then etc. So these are the mesoscale model products which are forecasting that, okay, East India is likely to get thunderstorm activity. IIRS I just showed you. Yes, East India is likely to get a lot of thunderstorm activity. Uh, we have here the scope nowcast for the same thing. So scope nowcast is showing. Now this is where we are using scope, and it gives some idea about the potential of scope as well as the weaknesses of scope nowcast. That means for very small regions, we are not able to correctly detect the accuracy of the cells growth, decay, as well as intensity. But it gives a good indication of where it is happening. So based on 9 UTC, you have the 0th minute, 60th minute, 120th minute forecast, and corresponding time 10 UTC, you can see it is a forecast. So what actually happened at 10 UTC was this, at 11 UTC was this. So some indication it is giving. That means large scale pattern is well detected by the satellite. Smaller scale, definitely there are problems. So we need to use this carefully. I did not discuss the upper level convergence, lower level divergence, vorticity pattern, etc. But this is the slide I was basically waiting for. Say this is showing the relative vorticity at 3 UTC, sorry, at okay, at 700 millibar and okay, at 700 millibar at 9 UTC throughout the figure. So what it really shows is that it's not 700 HPA, sorry. This is showing the top left is showing your 200 HPA 9 UTC picture vorticity. Middle one is showing 500 HPA relative vorticity at 9 UTC again, and lower bottom right is the 700 HPA relative vorticity. So what it really shows is that yes, there is a, and if you really compare this with the current, with the convergence and the divergence. Divergence is to the left, which is yellow, and convergence to the right, which is in blue. So 9 UTC throughout, if you see, it is indicating that there is an increase in the, over East India, there is an increase in the convergence in the lower levels. There is an increase, I did not show the evolution, but there is an increase in convergence over East India. Convergence, there is an increase in vorticity in the lower levels over East India. So everything is favorable for, if convection is happening, it is likely to increase. This is what was happening on this particular day. So Rapid is giving you very good Rapid tool of Insect 3D. It's a, I cannot, I mean, I cannot praise this enough. This is a particular tool which is very good for detecting and detecting the convective cloud as opposed to the cirrus outflows. So this is giving a good indication where the cloud top brightness temperature is increasing, is decreasing, and correspondingly which are the developing cloud patches. This is the RDT, which is giving you over East India, which are the locations where where the thunderstorm potential is more, and this is the actual lightning picture of where it is happening. So again, I'm saying these pictures are not to be seen in isolation, but as a part of the evolution of these parameters, how they're changing. We do not have any other source of data than satellites, which can give you sub-hourly scale evolution of weather systems uniformly, homogeneously throughout the country. So if you have to give any operational forecasts, satellite data forms an important backbone of what we use for forecasting. Definitely, at the end of the day, radar is the best tool for thunderstorm forecasting. So where the areas of convergence are there, where the cells will develop, all this will come from the radar data. Based on this, we are giving round the clock 3-hourly nowcasts for thunderstorms. You can see these are color coded based on impact, and for 1166 stations all over India and 732 districts of India, nowcasts are being issued. So This forecast, this nowcast, is being issued on the basis of the SOP which I discussed earlier. If we are to give hail warning, what is the color and how it is to be located, again through a more detailed SOP. So all those tools are being used in order to give a forecast. I think that is all. Please visit us at mausam.imd.gov.in. I hope to see some of you in IMD sometimes. Thank you.
Thank you, ma'am.